Hello and welcome back. In the previous lectures, we're talking about solution thermodynamics. And what we looked at so far is trying to define a property known as partial molar property for a mixture and then relate it to the total property of the mixture M via the summability relation, and then some of the relationships amongst the partial molar properties themselves. Now, while these are certainly helpful, they still do not give the complete picture of how a mixture behaves. Like we said earlier, there are more than 22 million compounds known in the process industry, and they form a large number of mixtures, and it is very difficult to characterize each and every mixture. So what we'd like to rather do is try to somehow relate the property of a mixture to its pure component counterparts. Or if I can obtain a relationship or predict the relationship between either M or Mi bar to Mi, what I'm looking for then is a relation between Mi bar or M and the pure component counterparts Mi. If I can somehow relate these quantities, then I can at least predict how the mixture is going to likely behave. To be able to do that, we start off with the easiest type of mixtures we can predict. Recall how we have dealt with PVT relationships. We introduced the ideal gases first, where the PVT relationships are fairly linear, and then we extended it to real gases. So we'll do a similar exercise here. When we talk about mixtures, the first thing we'll try to analyze is how the pure component Mi is related to the partial molar property Mi bar in case of ideal gas mixtures. So let's look at an example, what exactly we mean by an ideal gas mixture. Over here we have two gases which are separated by a wall in between, and at some time t equal to 0 we decide to remove this wall, and then the gases are going to mix freely. Before mixing, we have pure species 1, and the PVT relationship for this pure species 1 is PV1T is N1RT. So both these gases are at the same temperature and pressure even before mixing, and they are at the same temperature and pressure after mixing. Let's say these are ideal gases. Then for pure 1, PV1T will be N1RT, V1T being the total volume for gas 1, and for pure species 2, PV2T will be equal to the number of moles for 2N2RT. T and P are same. So now after I mix, all I have is a mixture, right? And for the mixture, PVT is N times RT. Right? Because the temperature and pressure are same and both gases are ideal, note that V1T over N1 is the molar volume for gas 1, should be equal to the molar volume of gas 2 because temperature and pressure are same and both gases are ideal, and that should also equal Vt over N, and let's call this as the molar volume V. All the three molar volumes for the pure individual pure species as well as for the final mixture is same. Let's call it as V, right? Now, if this is a mixture and I want to calculate the partial molar volume for this mixture, how do I get that? For the mixture, the partial molar volume V1 bar is the derivative of the total volume N times V over N1. I have only two components, so it is at constant temperature, pressure, and N2 is held constant, right? And recall that N is N1 plus N2. So derivative of n with respect to n1 at constant n2 is 1. So if I take this, the molar volume V is constant anyway, it comes out. Once the temperature and pressure are constant, molar volume V is constant, it comes out, and then I have derivative of n with respect to n1 at constant n2, which will be V, right? And similarly, V2 bar will also be equal to V. And notice that then for this ideal gas mixture, V1 bar will be equal to V2 bar will be equal to V, which is also same as the individual molar volumes for 1 and 2, V1 and V2. So this is an example for a binary gas mixture. We can extend it. In general, Vi bar will simply be equal to Vi for an ideal gas mixture. Now, we have demonstrated that the partial molar volume of an ideal gas of component I in an ideal gas mixture is same as the pure component molar volume. It doesn't depend whether there is other gas or not. Intuitively, it makes sense because ideal gas by definition has no size. The molecules of an ideal gas have occupy zero volume, and they do not interact with one another. So the molar volume will not change as long as the temperature and pressure are same. Now, what happens to something like internal energy, enthalpy or entropy, etc.? To answer this question, we resort to what is known as the Gibbs theorem. And according to the Gibbs theorem, the partial molar property Mi bar in a mixture at T and P is given by the pure component property at the same temperature but at its partial pressure Pi. So this partial pressure Pi is essentially the mole fraction times the total pressure, right? We call this as the Gibbs theorem. Essential idea behind this theorem is that once an ideal gas is in a mixture, and because of the properties of an ideal gas having zero volume and no interactions with one another, although the ideal gas is in a mixture, it behaves as if it is an individual component with its own partial pressure. It's not going to interact with the other species that is present in there. That's the idea behind the Gibbs theorem, and then the partial molar property is given by the pure component property but at its partial pressure. Now, we'll take this idea to estimate the other partial molar properties or thermodynamic quantities. The first one of interest is Ui bar at a given temperature and pressure. This will be Ui at its partial pressure Pi, right? The temperature is same, but this time the pressure has changed to the partial pressure. But for an ideal gas, this is an ideal gas. For ideal gas, U does not depend on pressure. It only depends on temperature, if you recall. So Ui bar Ig then at T and P is Ui Ig at T and Pi according to the Gibbs theorem, and this is same as Ui at T and P because it is independent of the pressure. And so the partial molar property for component I is same as the pure component property at the temperature and pressure of the mixture, right? Going by similar logic, Hi bar Ig at T and P, you can show that it will be same as the pure component property at T and P. And again, as long as the temperature is same, the enthalpy does not change, right? What these two relations for enthalpy and internal energy also mean is that for the mixture, the total molar property U according to the summability relation is Xi Ui bar, and because Ui bar is same as Ui, this will be same as Xi ui. Similarly, H is, oh, this is for an ideal gas alone, right? So we'll use this Ig to denote that we're talking about an ideal gas. Sorry, this we should write it as Yi for mole fraction. And similarly, HIIG is Yi, Hi bar Ig, which will be identical to Yi, HIIG. So for an ideal gas, all we need to estimate the property of the mixture is the pure component properties at the same temperature and pressure. As long as I have that information, I can directly calculate what the enthalpy and internal energy for the mixture are. I do not need any additional information. Now, what about entropy? According to the Gibbs theorem, SI bar for an ideal gas at T and P is SI at T and PI, right? This is at some composition Yi. Let's call this as SIIG at T and PI, right? Now, if you recall, at constant temperature, if you recall, ds for an ideal gas is minus R d ln P. So what I'll do is I'll take this and integrate it from the total pressure P to, or from the partial pressure Pi to the total pressure P. And if I do that, integral going from Pi to P, d Si Ig will be minus R ln P over Pi, right? If I do the integral on the right hand side and apply the limits, then it will be P over Pi. So it will be minus R ln P over Pi, right? So on the left hand side, what I have is SIIG at T and P minus SIIG at T and Pi will be, this difference will be minus R ln P over Pi, or SIIG at T and Pi will be the pure component value at T and P plus R times ln. Remember that mole fraction Yi is Pi over P, so P over Pi is 1 over Yi. So this will be 1 over Yi. So Si bar Ig at T and P will be Si, the pure component value at T and Pi, which is now the pure component value at T and P minus R ln Yi. I have inverted 1 over Yi and then brought the negative sign before R. So then for the partial molar property or partial molar entropy in a mixture of ideal gas, Si bar Ig will be the pure component value for entropy T and P minus R ln Yi. Now we can extend this. What we had earlier is Si bar Ig is SIIG at T and P minus R ln Yi. Now S is sigma Yi Si bar from summability relation. What this means is Sig will be sigma SIIG minus R sigma Yi ln Yi. Right. This is the total entropy of an ideal gas mixture in terms of the pure component entropy SIIG and the mole fraction Yi. Remember that this is at some temperature and pressure. This also is at the same temperature and pressure. So what we have done is in effect related the entropy of the mixture at a given temperature and pressure to the pure component entropy at the same temperature and pressure and the mole fractions, of course, for an ideal gas scenario. We can also write the Gibbs free energy, which is of more interest to us because it is related to chemical potential, and phase equilibrium problems depend on chemical potential like we discussed earlier. The Gibbs free energy, partial molar Gibbs free energy mu I Ig is same as the chemical potential, as you recall, and this will be Hi bar Ig minus T times Si bar Ig. Now if you recall, Hi bar Ig was Hi Ig. It is same as the pure component property at the same temperature and pressure minus T times, I'm going to replace this Si bar Ig here with this quantity here, right? So that will be Si Ig minus R ln Yi. So Gi bar Ig will be Hi Ig minus T Si Ig plus RT ln Yi, or this quantity here is Gi for the pure component plus RT ln Yi. So the partial molar Gibbs free energy, or the chemical potential, is equal to the pure component Gibbs free energy Gi plus RT ln Yi. So what we have done is derived a relationship between the partial molar property and the pure component property, all at the same temperature and pressure. Let's quickly summarize what we have done so far. Vi bar is Vi, Ui bar is Ui, Hi bar is Hi, right? Si bar is Si minus R ln Yi, and Gi bar is Gi plus RT ln Yi. Now all of these are for ideal gases, so I'm going to use the superscript Ig. We have derived all these relations for partial molar properties in terms of the pure component properties. All are at T and P. The temperature and pressure are same, which is same as that of the mixture. Now following these relations, we can also show that U is sigma Yi Uiig. We use the summability relation over the partial molar properties to get these equations. Sigma Yi Hiig Sig. The mixture entropy is sigma Yi Si Ig minus R sigma Yi ln Yi. And finally, the Gibbs free energy of the mixture is sigma Yi Gi plus RT sigma Yi ln Yi. So we have derived the partial molar properties as well as the total properties for the mixture of ideal gases, right? One final thing while we are at this is to define a property called as property change upon mixing. When we mix two substances, as we looked at the schematic earlier, this one, I have two different species, pure species, separated initially at some temperature and pressure, and what happens when I mix them? How much is the total property change? We call that as the property change upon mixing. So let's quickly write that quantity by looking at these equations here. So what I'll do is I'll draw that and write property change upon mixing. And the way we define property change upon mixing is the property of the mixture at T, P, and Yi minus the pure component properties weighted with their mole fractions also at the same temperature and pressure, right? So for sake of clarity, I'm going to drop the functionalities. This is simply M minus sigma Yi Mi. M as well as Mi are all taken at the same temperature and pressure. and the corresponding mole fraction for M is Yi, of course, right? So by looking at this expression, I can write property change on mixing for delta U mixing of an ideal gas is U for an ideal gas minus sigma Yi Ui. And because of this relation here, this automatically implies delta U mixing for an ideal gas is 0. Going through similar steps, I can also derive the following equations. Delta V mixing for an ideal gas is 0. Delta H mixing for an ideal gas is 0. The entropy of mixing, delta S mixing for an ideal gas mixture is minus R sigma Yi ln Yi. And finally, the Gibbs free energy of mixing for an ideal gas mixture is RT sigma Yi ln Yi. So these are all the various quantities. Of course, in the previous slide we derived internal energy change upon mixing is 0 as well. So these are various property changes upon mixing for an ideal gas mixture. Now that we talked about ideal gas mixtures, let's quickly run through two examples on using the equations we have just derived before we move on and extend this discussion on ideal gas mixtures to what are known as ideal solutions. The first example says we have a stream of nitrogen flowing at a certain flow rate and oxygen flowing as well, and these two streams, I have a stream of nitrogen and another stream of oxygen, and what we get out is a stream of air or a mixture of these two compounds. And we're interested in assuming the rate, we're interested in calculating the rate of entropy change for this particular process, right? To calculate the rate of entropy change, what we'll do is first find the molar flow rates of the two streams, right? So for N2, molar flow rate N1 dot is 22.148 kilograms per second times 1000 grams per 1 kilogram times 1 mole per 28 grams. So that will translate to 791 moles per second. Similarly, for oxygen, N2 dot is 209 moles per second. And the total molar flow rate for the mixture N, this is N1 dot plus N2 dot, this will be 1000 moles per second, sum of 791 and 209. This is the total mixture I'm making. And we are interested in finding the rate of entropy change. So delta S total dot will be N dot times S. Let's call these streams, let's give them some numbers, right? So let's call this as 1, this as 2, and this as 3. Then delta S total, the change in total entropy or the rate of that change, is N dot times S3 minus N1 dot times S1 minus N2 dot times S2. So this will be essentially N dot times S3, the molar entropy of stream 3, minus Y1 S1 minus Y2 S2 dot. And if you look at this, we can easily recognize that the quantity inside the parentheses here is the entropy change upon mixing, delta S mixing. So then essentially delta S total, this change or rate of this change is n dot times delta S mixing, the molar entropy change upon mixing. And that is what we're interested in calculating. I already know n dot. All I need to find is the entropy change upon mixing, and I can then calculate what I need. Now, by definition, if you recall, for an ideal gas mixture, we can assume that this is an ideal gas mixture. Delta S mixing for an ideal gas mixture is minus R sigma yi ln yi. So this will be negative 8.314 times y1, which is 0.791 ln y1, which is again 0.791 plus 0.209 ln of 0.209. And this quantity right here turns out to be 4.262 joule per mole Kelvin, right? And if I'm interested in the total entropy change, rate of total entropy change, total dot, then it is n dot multiplied with delta S mixing for an ideal gas, because we can assume the streams to be ideal gas streams in this scenario. This turns out to be 1000 moles per second multiplied with 4.262 joule per mole Kelvin. So that will be 4.262 kilojoules per Kelvin second. This is the rate of entropy change for this particular process. Right. Notice that the entropy change is positive, which it should be for a process. It should be positive. It's greater than 0. Let's look at another example. It can be shown that the minimum work of separation necessary to separate an ideal gas mixture is negative delta G mixing. This is the minimum work required to separate an ideal gas mixture. Now calculate the minimum work necessary to separate 1 mole of air containing 80% nitrogen and the balance oxygen. Of course, we can assume that in this particular scenario, we're talking about ideal gas mixtures. So if we were to calculate the minimum work required, W minimum then is negative delta G mixing of an ideal gas, right? And we're given that Y1 is 0.8, Y2 for oxygen is 0.2, and the temperature is 300 Kelvin, right? Now, for an ideal gas mixture, delta G mixing is RT, right? Sigma yi ln yi. So that will be negative 8.314 times 300 times 0.8 ln 0.8 plus 0.2 ln 0.2. This value right here turns out to be, so delta G mixing is a molar quantity, so the minimum work required is the minimum work per 1 mole of gas. So that's how we can use the concepts about ideal gas mixtures we learned earlier and do some quick calculations on entropy changes upon mixing and Gibbs free energy changes upon mixing. What we'll do next is we'll continue this discussion on ideal gas mixtures and extend it to a larger class of mixtures. The idea being, some of the characteristics of ideal gas mixtures can also be translated to dense phases, be it denser mixtures of gases or even liquids and solids for that matter, right? So let's extend our discussion on ideal gas mixtures to a new class of mixtures known as ideal solutions. In an ideal gas mixture, recall that the partial molar Gibbs free energy or the chemical potential is related to its pure component value via this equation. What we'll do is define a class of solutions or mixtures known as ideal solutions, which exhibit similar relationship between the partial molar Gibbs free energy or the chemical potential and the pure component Gibbs free energy. So GI bar in an ideal solution, ID standing for an ideal solution, is related to GI, the pure component Gibbs free energy, in exactly similar relationship. Notice that I have changed the mole fraction Yi to Xi. Yi is something we usually use for a gaseous phase. Xi is something we use for liquid phase. This class of mixtures is typically used to define liquid solutions. So I'm using Xi in this case, but the idea is that we have extended a characteristic of ideal gas mixture, that is a relationship between the chemical potential and the pure component Gibbs free energy, to denser phases, right? Be it a denser gaseous phase or even a liquid phase. In this case, the ideal gas relationship PV equal to nRT or other characteristics of non-interaction between the molecules or zero size of the molecules may not hold, but still the partial molar Gibbs free energy is related to the pure component Gibbs free energy in a similar fashion as that in an ideal gas mixture. So what this does is it gives the composition dependency for the partial molar property in terms of the mole fraction in a similar fashion as that in an ideal gas mixture. Now, it serves well for dense gases, liquids, or even mixtures of solids, as long as we call them as ideal solutions. And typically, it works well when the liquid mixtures have species that contain molecules of similar sizes and similar chemical nature. For example, adjacent species in a homologous series or isomers can be well defined using an ideal solution behavior. Now, because of this reason, right, so we can use the relationships we have developed earlier to calculate the other thermodynamic properties for an ideal solution. Now, we know that GI bar ID is GI plus RT ln Xi. Xi can be mole fraction either for gas or a liquid phase, like I said earlier. Now, if I want to calculate VI bar ideal, then recall that V is the derivative of the Gibbs free energy with respect to the pressure at constant T and X, right? And once T and X are constant, then this will simply be the derivative of GI with respect to pressure at constant. Well, let me write that explicitly. This will be derivative of GI plus RT ln Xi with respect to pressure at constant T and X. Now, because temperature and X are constant, the second term drops out and all I have left is derivative of GI with respect to P at T and X, which is essentially the molar volume for component I, VI. Now, notice that this molar volume doesn't have to be ideal gas volume. It is whatever the molar volume for component, pure component I at that temperature and pressure is. Next thing we want to calculate is the partial molar entropy in an ideal solution, SI bar ID. This is derivative of the partial molar Gibbs free energy with respect to the temperature at constant P and X. So this will be derivative of GI plus RT ln Xi with respect to temperature at P and X. In fact, this is negative of that quantity, right? So that will be negative derivative of GI with respect to temperature at P and X for the pure component minus R times ln Xi. All of them are constant. We only have temperature. So the derivative of temperature with respect to temperature is 1. The first term, of course, is the entropy of the pure species I minus R ln xi. Right. So what we have then is Si bar id is Si minus R ln xi. And finally, we can calculate the enthalpy Hi bar id. It is, since G is H minus Ts, H is G plus Ts, or it is Gi bar plus T Si bar id. So that is Gi plus RT ln xi plus T times Si minus R ln xi. So that will be Gi plus Tsi. That's for the pure species, and the other two terms cancel out. So that quantity will then be equal to Hi. So Hi bar id is same as Hi. So now let's quickly summarize what we have derived so far for an ideal solution. The first thing is Gi bar id. This is by definition of an ideal solution, is Gi plus RT ln xi. Then we have derived that Vi bar id is Vi, Si bar id is Si minus R ln xi, and finally Hi bar id is Hi. Now we can also write the property changes upon mixing. Delta H mixing for an ideal solution will be equal to 0 because it is H minus sigma xi Hi. Similarly, delta V mixing for an ideal solution will also be equal to 0. Delta S mixing will be minus R sigma xi ln xi, and delta G mixing of an ideal solution will be equal to RT sigma xi ln xi. So notice that all these property changes upon mixing are same as that for an ideal gas mixture. So what we have done is extended the concept of an ideal gas mixture to a class of solutions known as ideal solutions. And it turns out that the various thermodynamic property changes for ideal solutions are similar to what we have observed for ideal gas mixtures. So like I said, what it gives us is a handle on how to relate the property changes upon mixing or the partial molar properties to either the pure component properties or the mole fractions, right? So with that, we will stop the lecture today. When we come back in the next class, what we will do is try to extend this discussion on ideal solutions and see how we can apply them to real life problems. Thank you.